morning, students. Now, in the first lecture on electric potential, I made you understand what is the meaning of electric potential. So let's just revise the definition again. We said, what is electric potential? It is the work done to move a charge from infinity to a point. Make a test charge move from infinity to a point, work done to move from infinity to a point A per unit test charge, isn't it? That is the potential at A, and we reduce the expression of potential as, what was the expression of potential? We said it is KQ by RA, where RA was a distance from the given charge. So this is the formula we derived for electric potential. We reduced potential difference between 2 points. We said electric field is conservative in nature and thereby E is equal to minus dV by dr. Then we reduced electric potential at a point. Then we understood a very important concept, the last one, that is potential energy between a system of charges. A very important concept which I covered in class 11th also, and then I covered in class 12th in the last lecture. Now I'm taking the first a question on the concept of electric potential energy between three charges. If you recall the formula, you'll recall the formula when I do this numerical. I've taken three charges here. Three charges: a 4 coulomb charge at A, a minus 2 coulomb charge at B, a 2 coulomb charge at C on an equilateral triangle. Okay, I've taken an equilateral triangle of side 2 meter each. For convenience, I have not taken any other unit. I have taken only the SI system. Although 4 coulomb is a huge charge, still I have taken 4 coulomb charge. Now the question is, what is the potential energy of the system, or maybe what is the potential energy or the work done? Let's say, what is the work done to keep these three charges, 4 coulomb, minus 2 coulomb and 2 coulomb, on the vertices of this triangle, isn't it? So that's a question. So let's try to evaluate what the potential energy is, or what is the work done. So I'll write work done, that is work done by an external force, which is equal to the potential energy of the system is equal to K Q. What is Q1 here? Q1 is 4 coulomb charge into 4 into 2 upon the distance, that is 2. Okay, so that is the potential energy between a charge kept at A and charge kept at C, plus K, the potential energy between 2 coulomb and minus 2 coulomb. So 2, and this is minus 2, since the charge is negative and potential energy is a scalar quantity, so minus 2 upon the distance again is 2. Then the potential energy between 4 coulomb and minus 2 coulomb, K 4 minus 2 upon 2, isn't it? So when we find out potential energy, we find out potential energy between A and C, the potential energy between C and B, and the potential energy between A and B, and add them up. Let's see what is the result. K common, 2 common. This is what? This is 8 minus 4 minus 8, which gives me what? I'll get minus 2 K joule is the potential energy of the system. Okay, this is a work done by an external force to keep these three charges, station these three charges at the vertices of a triangle, isn't it? So one of the question in board exams, if I said in the last lecture also, we had this question in 2020 also, but the question was framed this way. The question was framed: what is the work done? What is the work done to break a system of three charges, that is 4 coulomb, 2 coulomb and minus 2 coulomb? What is the work done to break a system of these three charges so that the charges move to infinity? Okay, what is the work done by an external force to break a system of three charges kept on the vertices of a triangle? What you have to do is, you just have to find out the potential energy as you have found out. This is the potential energy. This is actually the work done to make the system. So what is the work done to break the system? Just change the sign of this sign of this potential energy? 2k. And what is k? 9 into 10 to the power of 9. So 18 into 10 to the power of 9 joule is the work done to break the system. So what you have to do is, if they ask you what is the work done to break the system, you find out potential energy of the given system, change the sign of the potential energy, you get the work done to break the system. Okay, so this is a question which was asked this year. Fine. Okay, let me take up one more question on the same concept, that is potential energy. Right now I took 3 charges, now I'll take 4 charges. Okay, I'll try to solve a similar question. I think this is clear to you. I'll try to solve a similar question, but now what I do here is, instead of taking 3 charges, let me try to find out what is the potential energy of 4 charges. Okay, what is the potential energy of 4 charges? Let's, again, for convenience, initially we take up a square. Okay, let's take up a square. Let's say I had a square here on which I kept a 4 coulomb charge. I have to keep a 2 coulomb charge, another maybe 4 coulomb charge, and maybe a 2 coulomb charge. For again convenience, I'll take all these distances as 2 meters each. This point is A, B, C and D. So the question is, I'll ask 2 questions. What is the work done to make a system, or what is the work done to place 4 charges, 4 coulomb, 2 coulomb, 4 coulomb and 2 coulomb on the vertices of a square of side 2, or what is the potential energy of the system of 4 charges placed on the vertices of a square? Both have the same answer. Let me try to find out what is the work done. So work done is equal to, I'll take this charge and this charge first, k into 4 into 2 upon 2, isn't it? Let me take this. Plus, you add the potential energy between 2 coulomb and 4 coulomb, k into 2 into 4 upon 2, fine, plus 4, okay, let me take this negative, just to introduce a negative term, k into 4, when you have a negative charge, you take the sign along with it, minus 2 upon 2, okay, so you have potential energy between these two, between these two, between these two, and between these two, plus k into minus 2 into 4 upon 2. Is that all? So we have taken potential energy between these two, between these two, between these two, between these two. No, we have to take the potential energy between the diagonal charges also. Remember the concept of potential, gravitational potential energy, same concept. So what do I do? First I try to find out what is the diagonal. Since it is a 2 meter side, so this diagonal will be root 2 root 2, isn't it? 2 root 2. Even this diagonal will be same. So what is the potential energy between A and C? That will be k into 4 upon 2 root 2. Remember, I am not taking square here, it's a potential, it's not an electric field. Plus the last term will be k into 2 into minus 2 upon again 2 root 2. So we can add them up. Let's simplify them. This will be k by 2. First I'll add these 4 terms. 8 plus 8 minus 8 minus 8. Oh, wonderful. Plus k by 2 root 2, 16 minus 4. So I think this goes off completely. So what I'm left with is k upon 2 root 2 into 12, or maybe 6 k upon root 2 joules. Fine. So this is the work done to make the system. This work is stored as the potential energy of the system. Okay. Now if they ask you a question, what is the work to break the system of 4 charges? What you have to do simply is work done to break is minus of u. So that is minus 6 by root 2 into k joules. Done. Fine. So that is the concept of potential energy between a system of 3 charges or a system of 4 charges. Fine. Okay, since I have taken up this example number 2, I'll also try to find out the potential maybe at the center of the square. I'll take O. The question is, what is the potential at the center, that is point O, due to these 4 charges? Remember, potential is a scalar quantity. So when I superpose potential, I need not use scalar. It's a simple mathematical addition, okay, algebraic addition. So what is potential at O? So I'll say potential at O, VO, let me name it, which is potential due to A plus potential due to B plus potential due to C plus potential due to D. Due to A, due to B, due to C, due to D. So what is potential due to A? K, Q is 4 upon OA. Okay, this point is A. Now this what will be this distance? Since the whole diagonal is 2 root 2, so OA distance will be 2 root 2 divided by 2. So this is root 2, even this is root 2, this is root 2, and this is root 2. Fine. So K 4 upon root 2 plus K 2 upon root 2 plus K 4 upon root 2 plus last one is this K minus 2 upon root 2. Remember, I have to take the sign of the given charge. Whatever sign of the charge is given, I have to take the same sign in the potential. This term goes off. This is same, so I think this will be 8K upon root 2. And what will be the units? Units will be volts. So potential at O is 8K by root 2 volts. So we did the concept of potential energy between a system of charges. We also found out what is the potential at the center of a square. Similarly, I can even find out what is the potential at point A. Say I have to find out potential at point A. Potential at point A will be what? Potential due to 2, potential due to 4, and potential due to minus 2. So K 2 by 2 plus K 4 by 2 root 2 plus K minus 2 by 2. Right? So at any point I can find out the potential. Clear? I think I'm clear with the concept of potential energy between system of charges, and also how to superpose potential. Remember, when you superpose forces, use vectors. When you superpose electric field, use vectors. But when you superpose potential, it is a simple mathematical addition. Fine? Clear? Okay. So with this concept of potential energy, I'll try to move on to another very important concept, that is concept of a dipole. The derivation has been asked a number of times in board exams. I'll try to find out the potential at a point due to a dipole. Okay, I'll try to derive the expression of potential at a point due to a dipole. If you remember, we already deduced the potential on the electric field on the axial line of a dipole. We deduced the electric field on the equatorial line of a dipole, and I gave you the work of finding out electric field at any journal point and at a distance of r, an angle of theta from the dipole. Now what I'm trying to derive is not the electric field. I'm trying to derive the expression of electric potential at any journal point due to a given dipole. Understand what I'm trying to do here. First of all, I'll choose a dipole here. Let's say a dipole minus Q and plus Q. That's a given dipole. Dipole moment, if I mark, the dipole moment is from negative to positive. This is the dipole moment. This is the center of the dipole O. What I have to do is, I have to, let me take this side as A. From this O, I have chosen a point, maybe point Z. Fine. Z and I have to find out what is the potential at Z. That's my question. Derive the expression of potential at Z, Z which is at an angle of theta with the dipole moment at a distance of r. Fine. Let me choose this point as A, this side as B, this distance is RA, this distance is RB. Okay. Now, according to so potential at Z I have to find out according to principle of superposition. Potential at Z is what? It is potential due to A plus potential due to B, isn't it? Simple superposition. Potential at point Z will be potential due to A plus potential due to B. Notice potential due to A at Z. I think potential at Z due to A will be K minus Q upon AZ distance which I have taken RA plus K Q upon PZ, right? So V at Z is equal to K Q, I'll take common, this will be 1 by BZ minus 1 by AZ. Okay, notice BZ here, BZ is this distance and AZ is distance. I make a small construction here, a very small construction. I extend this line and drop a line from A onto this line, mark this point as C. Now the C is marked in such a way that your AZ is almost equal to CZ. Okay, try to understand this. I'm extending this line, dropping a line from A on this in such a way that this AZ is equal to CZ. Okay, now this angle is theta, this angle is also theta. If this is A, can I say this OC length, this OC length is nothing but A cos theta. This OC length is A cos theta. I hope I am clear. This is A, this is theta, so this is A cos theta. So what is CZ for us? CZ is nothing but ZO plus OC. ZO plus OC. What is ZO? ZO is R and OC is A cos theta. In short, your AZ is roughly equal to, it's not exactly equal, it's roughly equal to R plus A cos theta. In a similar way, what I do is I drop a line from the B charge onto the ZO length such that this is almost equal to this. Fine. So I'll take BZ is almost equal to, I'll mark this point also, this is C, we mark this as D. Okay, so that is equal to DZ. BZ is equal to DZ. And what is DZ equal to? DZ is equal to ZO minus OD. And what is OD? If you again clearly look at OD, this is A, this is theta, so OD will be A cos theta again. So I'll write this as, this is ZO, ZO is R minus A cos theta. So that is your BZ. So what I have done here is, I have found out two expressions, one of AZ and other expression is BZ. Let me substitute these two expressions in my main expression of potential. What is the main expression of potential? VZ, which is equal to K into Q. VZ is R minus 1 by R minus A cos theta minus 1 by R plus A cos theta. Right? So I can solve this now. K, Q, this is R plus A cos theta minus R minus plus A cos theta upon R square minus A square cos square theta. Isn't it? So LCM is R minus A cos theta into R plus A cos theta. So I get R square minus A square cos square theta. Right? Fine. Let me solve this. R cancels out. This gives me what? This gives me K, Q, 2A cos theta upon r square minus a square cos square theta. That is potential at Z. K Q 2a cos theta. Now what is Q into 2a equals to? We know it is equal to P. Dipole moment is Q into 2a. So my general expression of potential therefore comes out as K P cos theta upon r square minus a square cos square theta. That is my general expression of potential at any point due to a dipole. So what I am getting here is I am getting Vz is equal to K into dipole moment into cos theta. What is theta? Theta is the angle between r and the side 2a, the distance between the charges, r square minus a square cos square theta. So if you are lucky enough, you will get a direct 3-mark question in board exams, or they may ask you, they may not ask you directly potential at any point. They may ask you what is the potential on the axial line of a dipole, 1-mark question. What is the potential on the axial line of a dipole? So what we do here is we take a special case of this. What is the special case here? Special case 1, I'll take theta equal to 0. If I take theta equal to 0 means what? This is theta. If I take theta equal to 0, that means this point Z shifts on the axial line. This is nothing but your axial line. Or maybe they may ask you what is the potential on the end-on position of a dipole. This is the end-on position also. If you put theta equal to 0 here, Vz clearly is equal to K P cos 0 upon r square minus a square cos square 0. Cos 0 is equal to 1. So what I get is K P upon r square minus a square. That's my first special case, that if theta is equal to 0, find the potential on the axial line of a dipole. So on the axial line of the dipole, K P upon r square minus a square. If you remember what is the electric field on the axial line of a dipole, K 2p upon r cube. I'll repeat, K 2p upon r cube is the electric field on the axial line of a dipole. Potential on the axial line of the dipole is K P upon r square minus a square. Okay. Second case, I can take theta equals to 90 degree. So when I take theta equals to 90 degree, this theta is 90. So I jump to the equatorial position. So remember what is the electric field on the equatorial position? Electric field on the equatorial position was K P by r cube, right? But if you carefully look here, if you put theta equal to 90 in this expression, we get Vz cos 90 0. Oh wow. So electric potential on the equatorial line of the dipole is 0. A very important fact. Very important fact. If you choose the equatorial line at any point on the equatorial line, the potential due to the dipole is 0. You need not do the whole derivation to prove this 0. It would have straight away been proved. If you choose any point on the equatorial line, the distance would have been same, x and x, isn't it? So at any point on the equatorial line, the potential would have been K minus q upon x plus K q upon x. Both the terms would have got cancelled. So a very important deduction that comes to you is you got a position where electric field is never 0, right? Like what was electric field at this position? Electric field, I'll write it here. If you can see, E on the equatorial line was K P upon R cube, isn't it? K P upon, this is electric field on the equatorial line, whereas potential on the equatorial line is 0. So the question might come, which is a position where electric field is never 0, however the potential is always 0. So due to a dipole, so that the position is the equatorial line of the dipole. Or maybe they may ask you, draw the equipotential surface. I'll come to that topic in the coming time, but draw the equipotential surface. Or what is the equipotential surface due to a what is the equipotential surface due to a dipole? Now this position is the equipotential surface. Equipotential, same potential. So on this equatorial line, at every point the potential is same. So it is an equipotential surface also due to a dipole. Fine. So this is an important topic. You need to learn the final expression also, and you need to understand the potential on the axial line as well as potential on the equatorial line due to a dipole. Fine. I hope I am clear. If you check out your NCERT, you have the same derivation in NCERT, but probably they have used a different approach to derive it. If you like that approach, you can do it, or you may use this approach to derive the expression at a point due to a dipole. Fine. Okay. So that is my important topic which I want to discuss in this lecture. There's another topic which I like to cover today in this lecture on electric potential. And what is that topic which I am going to cover? The next topic is write down the topic as equipotential surfaces only. A very important topic. Write down the topic as equipotential surfaces. I think you remember we discussed what are Gaussian surfaces. What are Gaussian surfaces? Just recall Gaussian surfaces. We discussed what is a Gaussian surface, isn't it? Gaussian surface. I'm sure you remember what is a Gaussian surface. Still, I'll just state it again. A Gaussian surface is an imaginary surface around a given charge or a charge distribution at every point on which the electric field remains constant. And we said a Gaussian surface has to be a closed surface. It should enclose some charge, and electric field intensity should be constant at every point on the Gaussian surface. In a similar thought, we have another concept of equipotential surfaces. So what is an equipotential surface? As the name suggests, equi matlab same, potential obviously, electric potential they are talking about. So equipotential surfaces means surfaces on which the potential remains constant. Right? The surfaces, imaginary surface on which the potential remains constant. Let's say if I take a point charge, I'll take a point charge, isn't it? So if I take a point charge, on the point charge, and I have to draw the equipotential surface, definitely I can draw KQ by R here, KQ by R here, KQ by R here. At every point on this surface, the potential will be constant, isn't it? If I take a point charge, we'll have a spherical equipotential surface. And how many equipotential surfaces we can draw around a sphere, around a point charge? I think we can draw infinite equipotential surfaces around a point charge. Now, the question that is asked in the board exams, was it asked this year? I don't think so. The question was a little different. I'll discuss that question also today. But the question that is asked is, draw the first three equipotential surfaces due to a point charge. Okay, you can note down the question. Draw the first three equipotential surfaces due to a point charge. Now the question seems so simple. Most of the kids, what they do is, let's say we have a point charge, surface number 1, surface number 2, surface number 3. Electric field, brilliant. So this is electric field and this is your EP surface. They're so happy they've answered the question correctly. But my dear friend, this is not how it has to be drawn. This is not how it has to be drawn. You have to be careful. When NCERT people ask you a question, there's a logic behind the question, right? So the question is, draw the first three equipotential surfaces due to a point charge. I'll put another question. The answer of both will be same. In fact, you can put all these questions as a points in the properties of equipotential surfaces. We will discuss it this way. Equipotential surfaces. So I'll discuss the properties of equipotential surfaces. Put down this heading. Properties of equipotential surfaces, and the first property is the distance between equipotential surfaces goes on increasing as we move away from a point charge. I hope you can recall that when you take a point charge, the electric field produced by a point charge is variable. It is not a constant electric field. So I'm taking a point charge here. Okay, I'm taking a point charge here. Let me take a point charge here. Q. The electric field goes this way. So when I discuss this property, you get the answer of the question which I put forward. That draw the first three equipotential surfaces due to a point charge. The property is the distance between EP surfaces goes on increasing as we move away from a point charge. Now, how does this happen? E is equal to dV by dr, isn't it? If I take mod of this, E is equal to dV by dr. Now, if I take dV constant, can we say E is inversely proportional to dr? Of course we can say this. Or maybe dr is inversely proportional to E. Right? So when you take a point charge, let me draw the first EP surface. Let's say this is the first EP surface, EP1. If I have to choose another EP surface, the second EP surface, what I am trying to tell you here is this distance, if this is dr1, this distance is dr2, and if I draw the third EP surface, then this distance is dr3. Very clearly what I am drawing here is dr3 is greater than dr2 is greater than dr1. But what I have to take care of is the potential difference between these two surfaces, which is dV, is same as the potential difference between these two surfaces. That is, if I keep the constant potential difference, if I keep dV constant between EP surfaces, this dV is equal to this dV is equal to this dV, then dr is inversely proportional to E. Now that means what? If E decreases, obviously dr increases. So when we move away from the point charge, E goes on decreasing, so dr goes on increasing. E decreases, so E decreases, dr increases. So if dr increases means what? The distance between successive equipotential surfaces go on increasing, right? So if they ask you to draw three equipotential surfaces, do not draw them equal spaced. The spacing will go on increasing, especially when electric field is not constant, electric field is variable. A variation will come if you have constant electric field. Let's say if I have a sheet of charge, right, thin sheet of charge. So what is the electric field produced due to a thin sheet of charge? We know the electric field is constant. Due to thin sheet of charge, electric field is constant. So if electric field is constant, obviously dr has to remain constant. So if I draw EP surfaces, obviously the EP surfaces will be equally spaced. Why? Because E is constant. E. So dr. So if you have E uniform field, the spacing remains constant. But if you have non-uniform field, the spacing goes on increasing. Right? So that is the first property of equipotential surfaces. Fine. I hope I'm clear with this. I'll shift on to the second property of EP surfaces, the second property of equipotential surfaces. You can write down the property. The second property is equipotential surfaces. You can put it this way. You can put it this way. Electric field is always perpendicular to the equipotential surfaces, right? I think we had discussed this point during discussion of properties of electric field, that electric field emerges or terminates on the surface of the conductor perpendicularly. Now we are trying to justify that whenever electric field originates from a equipotential surface, or when it terminates to equipotential surface, it is always normal. And mind well, very well, a metallic conductor, if you take a metallic conductor, any conductor, maybe a copper wire or any other metallic conductor, the surface of a metallic conductor is always an equipotential surface. The surface of a metallic conductor is always an equipotential surface. That is why you do not see the flow of charges till we apply a potential difference, isn't it? If you do not apply a potential difference, the charges will not move. So the charges do not move. That means at every point the potential is same, isn't it? So the question that can be asked in your exams is this way also, that prove that electric field originates normally to the surface of a conductor, or normally to the surface of an equipotential surface. So let's say this is the second property which I am discussing, that EP, the electric field, is perpendicular to EP surface. Fine. So let's say I choose a EP surface here, a charge here. Let's say this is electric field going here. I keep a test charge on the EP surface. If I keep a test charge on the EP surface, if I try to displace the charge tangentially to the EP surface, if I try to move the test charge tangentially to the EP surface, what is the work done in moving this test charge on the EP surface? We know dW is equal to F into dr, isn't it? F dot dr, or maybe F dot dr is work done to move the test charge on the EP surface. But what is F here? F is equal to Q into Q0 into E. So Q0 E dW, right? Fine. So dW upon Q0 is equal to E dot dr. Now what is work done per unit test charge? I think that is what your dV is, potential differences. We discussed at length. Now we are saying that the surface is an EP surface, equipotential surface. On the EP surface, what is change in potential? We say but change in potential definitely will be 0. So 0 is equal to E dot dr. That means E is perpendicular to dr, isn't it? And what is dr? dr is a displacement at any point on the EP surface. So we justify that electric field is perpendicular to the EP surface, right? So that is my second property of EP surfaces. I'd like to mention another property here. You can quickly note down. You can note down work done in moving a charge on EP surface is always 0, right? Work done is always 0. Now, what is work done in moving a charge on the EP surface? We know that dW work done is nothing but Q into dV, isn't it? Potential difference between 2 points into Q, the charge which I am keeping, maybe Q0 I'll take, gives you work done. But what is dV on the EP surface? Again, EP surface, when I say dV is equal to 0. So dV is 0, that means work done is equal to 0. Work done in moving a test charge or maybe any other charge on the EP surface is 0, because the potential at every point is same, and mind you, potential is same. Potential difference multiplied by charge will give you work done, isn't it? Okay, so that is the third point. Fourth, you can write the property as potential at every point on the EP surface is constant, right? So these are a few properties of EP surfaces. I hope I'm clear with the concept of equipotential surfaces. Now another topic, last topic, which I'll discuss today. In fact, this is the last question. This is a question which has been asked in 2020 boards, which is based on the concept of potential. This year they had asked questions mostly on the potential only. So this topic is quite important. It is given in the NCERT textbook. You can write the heading, a very small concept. Write the heading: what is the potential energy? What is the potential energy? What is the potential energy between two charges Q1 and Q2? Two charges Q1 and Q2, if they are placed, potential energy between two charges Q1 and Q2 if they are placed in external uniform electric field. Okay, if I take external uniform electric field, that is potential energy between two charges Q1, Q2. This is boards 2020. 3 marks or 2 marks? I don't exactly remember, but let's say 3 marks. Two charges Q1 and Q2 placed in external uniform. I'm taking uniform, okay? Uniform electric field. Who produces uniform electric field? A sheet of charge. A sheet of charge can produce uniform electric field. Let's say this is a given electric field. This is the last topic for today's lecture. Let's say there's a sheet here, maybe a positive sheet. You can imagine a sheet here. This is electric field which is uniform. Fine. Now, electric field is uniform. Let's say I bring a Q1 charge from somewhere, from infinity, and I have to place it here at a distance of R1. At the distance of R1, I have to place Q1. So what is the work done to place Q1 in the external field at R1? I think you all will agree that the work done will be equal to Q1, which I am bringing, into potential at 1. Right? So if I find out potential at 1 and multiply by Q1, that will be the work done to place Q1 at this point. Now what is potential at 1? Very clearly I can write potential at 1 will be equal to R1 into E1. Now how did this come into picture? We know that E is equal to dV by dr, that is non-uniform electric field, but when it is uniform electric field, E is equal to V by R. Straight away you can use this. So V is equal to R into E1. So that is work done. Q1, E1, R1 is the work done to place the first charge at the given point in the external field. Okay. I have another charge Q2 here, which I have to place maybe somewhere here.